Imagine trying to engineer a city of 36.6 million people. Every day, the street-level infrastructure absorbs an overwhelming volume of traffic, friction, and heat. Now, pave 80% of that city in impervious asphalt and concrete, and drop a monsoon on it. The water has nowhere to drain. A typical flooding event here doesn't clear in hours. It stalls the city for 16 days. Above ground, the air routinely carries 5 times the WHO limit for particulate matter. The city sits near an active tectonic zone, yet you can't just widen a few storm drains or patched cracked roads when the math of intensifying monsoons and skyrocketing energy demand completely outpaces the repairs. This diagram maps out an alternative, APHQI 10.0. A $5.2 billion framework fusing quantum AI with heavy civil engineering. It treats the city as a living machine. 10 interdependent layers are orchestrated together, linking deep underground utilities to surface mobility and rooftop grids. To see how you install an operating system of this magnitude into a living, breathing metropolis, we have to look at how it rolls out phase by phase, from the precarious baseline of 2025 up to the year 2041. The first phase targets a 50 square kilometer pilot zone in 2027, and the immediate priority is the neutralization of the catastrophic water crisis. This predictive topological heat map is generated by an AI model trained on 15 years of local rainfall and streamflow data. By calculating thousands of variables, it maps out precise flood risks up to 3 days in advance with 94% accuracy. When the rain does hit, the physical streets respond. Standard asphalt is replaced with permeable concrete. These roads act like massive urban sponges, absorbing 2.8 millimeters of water per second and cutting peak street runoff by 90%. At the same time, the framework addresses the seismic threat. An array of sensors continuously feeds vibration data to a neural network, pinpointing microscopic structural anomalies in milliseconds. This schematic illustrates the defense against tremors. Rigid concrete frames are retrofitted with structural fuses, metal elements absorbing 80% of seismic energy. Post-quake, the main building remains intact. A damaged fuse is swapped in 24 hours, completely bypassing months of expensive retrofitting. By combining these software and hardware layers, Phase 1 proves we can decouple natural hazards from infrastructural disasters by predicting the threat computationally and engineering elasticity into the physical city. By 2030, the blueprint scales across the rest of MetroDaka. With the acute physical threat stabilized, the network shifts its focus towards solving the city's chronic resource and waste deficits. In 2025, the city produced 6,000 tons of solid waste every single day, with the majority of it routinely landfilled or burned. Phase 2 creates a new circular economy loop. AI sorts the debris, plastics are converted into fibers for stronger roads, and organic waste feeds digesters, producing 1.5 million cubic meters of biogas. That biogas joins a decentralized energy matrix targeting 90% renewables. The system harvests power from every available surface, utilizing bifacial solar panels, micro wind turbines, and agrovoltaic farming. Directing this complex web of power is the federated learning AI. It orchestrates 10,000 energy nodes in real time, shaving peak grid demand to prevent failures. Treating waste as a localized resource and energy as a decentralized network transforms the city from a fragile consumption sink into a self-sustaining ecosystem. In 2041, we can finally evaluate the massive $5.2 billion initial investment required to start this journey. Despite that high entry cost, the framework generates a 20-year net present value of $15.4 billion. These returns stem from a 65% avoidance of disaster losses and a 42% reduction in daily operational expenditures. Savings are realized when infrastructure no longer washes away and maintenance is driven by predictive AI. The physical transformation is just as stark. Flood events are reduced to 1 or 2 days. Seismic risk is cut by 71%. Carbon emissions have plummeted by up to 60%. The data from this 15-year deployment proves that engineering a city for climate resilience is a highly profitable economic strategy. Because this blueprint is parameterized, 85% of its architecture can be directly transferred to other at-risk cities globally. This operational nerve center gives city managers the power to oversee and continuously adapt this massive living infrastructure network in real time. By transforming is the definitive survival blueprint for the entire global South.